Okay, so let's do an example involving the fundamental theorem of algebra. Here's one where we have an even degree function, so a fourth degree polynomial. And remember that whatever the degree of the polynomial is, this is telling you how many zeros there are. Okay, there are 4 zeros to this expression. This problem in particular talks about the rational zero theorem and Descartes' rule of signs. We're not going to cover these. Okay, we have technology to kind of assist us with some of this. Rene Descartes did not, so he had a different method of going about this. It really adds a lot of work to our plate that isn't really necessary. It says possibly graph the polynomial as an aid in obtaining the first root. Okay, remember again that the word root is a zero, right? And zeros are x-intercepts. So it's possible when we graph this that we're going to see all 4 zeros as real numbers on the x-axis, okay? So I've already taken the liberty of graphing this function for us, and we see one intercept here at 2. We see another one at 3.5, okay? If we zoom out, now there's 2 intercepts, right? There should be 4 because there are 4 zeros. Now, if I keep zooming out, we don't see that graph turn back over and come back and cross again. And these are also crossing the x-axis, okay, which means they have an odd multiplicity. So each one of these, okay, either counts once or 3 times, right? So maybe this one counts once, maybe this one counts 3 times, but we won't know that right away until we put a little bit of work in. But we know 2 of our zeros, and that's what's most important. Now, the assumption is because we don't see any other intercepts happening, okay, the assumption that we have to go off of is that the other 2 zeros are complex, right? So that's what the fundamental theorem of algebra tells us. There's 4 zeros. So right now we've seen 2 x-intercepts, okay? And those x-intercepts were at 2 and 3.5, okay? We're missing the other 2 intercepts. We're missing the not necessarily intercepts, but zeros, right? Okay, so how do I find these? Well, if I know 2 of these zeros to be intercepts on the graph, I can do synthetic division with them. And what we have in this function to determine something a little bit easier to factor. So think about this broad scale, okay? We have 2 zeros. I can do, and you've seen this in a previous video, I can do synthetic division back to back, okay? And here's the idea. Stay with me. I'm going to end up with a 0 remainder here. At least I should if I do this correctly, because I know 2 is a 0. I'm also going to end up with a 0 remainder in this space. Now, when this starts as 2x to the 4th, remember how synthetic division works, right? We drop this number down. Now this 2 is 2x cubed, right? And what's going to happen is I'm going to drop this down. And when I drop this 2 all the way down to here, it went from 2x to the 4th. This is 2x cubed, right, after one round of division. After this second round of division, this is 2x squared. So this is going to end up being a quadratic. And when we get quadratics, we got different tricks that we can pull out, right? So I'm putting this 2 here, and I got ahead of myself. So if it's all right with you guys, I'm just going to erase this. I'm going to erase this too, because I don't want to have to fit the whole thing in here. So here we go. We drop the 2. 2 times 2 is 4. Negative 11 plus 4 is negative 7. 2 times negative 7 is negative 14. We add here. We get positive 12. 2 times 12 is 24. We add here. We get negative 42. 2 times negative 42 is negative 84. And here's that 0 remainder I was talking about. All right. Now, when we saw this as an x-intercept, right, and x-intercepts are zeros, we better get a 0 remainder because we're saying, yes, this is divisible by x minus 2, right? So again, so now we know, therefore, x minus 2 is a factor, right? Because if we divide by a number, if we do synthetic division by a number and we end up with a remainder, we put that number as a 0 in this factor. Now, we also saw that x-intercept of 3.5. So we drop this number 2 down. 3.5 times 2 is 7. We add, we get 0. We multiply, we get 0. We add, we get 12. We multiply. 3.5 times 12 is positive 42. We add, we get 0. Okay, so again, we should have gotten 0 because we know that 3.5 is one of our zeros. And if 3.5 is a 0, then x minus 3.5 is a factor. Okay, and what are we left with? So we have two of our factors. So here's where we currently stand. This function, this behemoth up here, okay, we know that one of its factors was x minus 2. We know that another factor was x minus 3.5, and it wanted the other two zeros. Well, what was the result of this? Again, come back to this idea. This was 2x to the fourth. This, when it drops down, every time we do a round of division, the degree drops by 1. So this was 2x squared. And this is our x term, which doesn't really exist. And this is that 12. So this result, that quotient really, is 2x squared plus 12. Okay? Now, from here, they want to know, right? What did they say? Find all roots. Find all roots, meaning find all zeros. So if I set this equal to 0, I've got this factor, I've got this factor, and I've got this factor now, 2x squared plus 12. Now remember what we said about finding zeros. We said if the product, right, because I'm multiplying this times this, which is in turn being multiplied by this, any one of these factors could be 0, right? So that's why we always go off to the side. We say x minus 2 could equal 0. Now, we're gonna skip past this because we know that 2 is the 0 from this term, from that binomial. We know that 3.5 is already the 0. This is the key right here to finding those other two zeros that we need, right? How do I know it's going to have two zeros? Because there's 4 zeros in this polynomial. 2 of them have already been found. 2 of them have not. This is where we get those other two zeros. So set that term equal to 0, set that binomial equal to 0 and solve. Subtract the 12 from both sides. Then divide both sides by 2. We get x squared equals negative 6. And because we've expanded our point of view to involve complex and imaginary numbers now, when I take the square root of this and the square root of this to get x by itself, I get x equals the square root, positive and negative. Remember, when we take the square root, we include both. The square root of negative 6. Now, sometimes we could leave it like this, but what's more proper is, remember, this is really the square root of 6 times the square root of negative 1, and negative 1 is I. So, long story short, when you have a negative square root, pull out this I and call it a positive, right? So here are the other two zeros. One of them is positive I radical 6, and the other one is negative I radical 6. So these are the other two zeros that we were missing from the beginning. And these are complex zeros, okay? Even more in detail, they are complex conjugates. These numbers aren't going to show up in my graph, okay? This graph is the real number system. Real numbers for x, real numbers for y, okay? So complex numbers don't show up in this graph as intercepts. So that was the key right from the beginning, right? We said, well, this is a 4th degree polynomial. I should see 4 intercepts, but I only see 2. That was a tip that was a tip off right there to say, hey, you know what? These other two zeros, they're probably complex. The only way to see those is by doing this division, okay? And then we get something that can either be factored or solved by setting equal to 0 at the end. I will say this at this point, we got lucky with this because there was no b term, okay? Come back to this for a second. If we end up here, you may, with a quadratic factor, you may have to use the quadratic formula in this case. We didn't have to, we got lucky because there was no b term. We could just isolate the x term. But if there was a, 2x here, that would mess things up. That would give us a little bit more work. We're lucky we didn't have that case. Okay, but we got our 4 zeros by graphing, synthetic division, and then solving.